All right, this is section 5.2, exercise 4. So we're given a function which is, probably unlike things you're used to. Basically, it's an accumulator function. So it's a function that is defined on a definite interval. So let's just kind of rewrite this off to the side so we can do some manipulations to it. So this function integrates from 2 to some value x. So x is the only variable here. So let's talk about if I'm saying x is the only variable, then what is t doing? Let's do this. Let's actually talk about what happens if x is equal to 2. So f of 2 is equal to the integral from 2 to 2 of g of t dt. So now that I've used a specific value for x, let's talk about what t is doing. Basically, what t is going to do is it's going to start at 2 and integrate this function g, which is what this blue curve is. It's going to basically start counting, measuring the area between that curve and the x-axis as I count towards the upper value, which, in this function is the generic x, but we're evaluating it at 2. So one of the properties of integrals we've talked about so far is that, if you integrate a function from a point to the same point, I don't care what the function looks like, that integral is equal to 0. Because essentially, if you're not allowing x to vary, how can you be accumulating any area? So here's one thing I do know. I know that f of 2 is equal to 0. So that's a base point we can put here. So let's actually mark this value on our blue graph here. So if f of 2 is equal to 0, let's kind of do what we've done in the past. Let's move left and right there from there and see what happens. Let's move to the right from 2, so from x equals 2 to x equals 4. So what is going to happen there? So let's talk about that. What is f of 4? F of 4 is equal to the integral from 2 to 4 of g of t dt. Another reason we use t is that because, let's put this in here, if we were to use x here, then essentially you have the variable x doing too many different jobs. Not only, so x is only meant to stand in for basically the upper limit to this integral. We shouldn't also have it, as the input to the function g, because g is the function that accumulates, basically integrates all the values from x equals 2 or from t equals 2 to t equals 4. So essentially, it's not important that we use t, it's just important that we don't use x again. Basically, we already have the variable x doing something. So what is the value of this integral from x equals, or t equals 2 to t equals 4? So essentially what I'm looking at here is, what is this area? So one thing we're told is that area 2 is equal to 12.75. So because of that, I think this value should be something less than 12.75, but can we do better than that? So assume further that the portion of A2 that lies between x equals 0.5 and x equals 2 is 6.06. So this right here, this left portion of that area 2 is 6.06. So I think because of that, we can say that the value of this integral is 12.75 minus 6.06, which comes out to 6.69. Okay, so that was a lot of me talking. So what do we just find? I think we found another value for this function f, which is at x equals 4, the value of this function is 6.69. So let's put a point there. Now, what is happening between these points? Do I connect it with something that looks like this, or is it linear? Can we say anything at all about that? Well, at the start of this subinterval, where x equals 2, our function this function g is at a maximum. So what does that mean about how it's accumulating area? Basically, the rate at which this function f is accumulating area will be at its highest. So while g is decreasing, this function will be still accumulating area positively, but it will be doing so at a less significant rate. So I think that I can connect these 2 points with a curve that has two vertical that looks like this. Let's make it a little more obviously concave down. Oh, something else I know is that at x equals 4, I'm going to stop accumulating positive area. So because of that, I have to have a maximum. Why is that? Well, what's going to happen between x equals 4 and x equals 5? I'm going to be accumulating area, but that area is going to be below the x-axis. So that area there I have to treat as negative. So now let's do this. What is f of 5? F of 5 is equal to the integral from 2 to 5 of g of t dt. Which we can say this. That's equal to the integral from 2 to 4 of g of t dt plus the integral from 4 to 5 of g of t dt. The integral from 2 to 4 is something I just found. That is 6.69. What is the integral from 4 to 5 of this function? Well, that is going to be whatever we're told area 3 is, which is 0.36. So 6.69 minus 0.36, which is equal to 6.34. 6.34. So from 4 to 5, it's going to be a very small thing here, but I'm going to decrease a little bit. All right, so we know at x equals 5, my function f is going to reach this point of 6.34, but can we be more specific about how it's going to reach that point? So at about 4.5, x equals 4.5, that's when I reach a relative minimum for g. So that is where my function is going to be, losing area most rapidly. So I think for the first half of the subinterval from 4 to 5, I'm going to be losing area at a more significant rate. And then it's going to change concavity halfway between over that interval, which is really hard to portray here, but if only my drawing tablet would stop fighting with me. Okay. I think that's actually pretty good. So again, so for the same reason I said for area 2, think about what happens with the accumulator function, with this integral function, as I go from x equals 4 to x equals 4.5. G is decreasing. It's negative and decreasing, which means I will be losing area at a decreasing rate. My area will be decreasing at a decreasing rate. But from x equals 4.5 to 5, my area will still be decreasing, but that rate will be, diminishing. So that's why I go from at about 4.5, I have an inflection point. My area goes from, so I'm still everywhere between x equals 4 and x equals 4.5. My area is decreasing, so f is decreasing with the concavity changes in the middle. So now from there, what can we say about the last area? So from x equals 5 to x equals, is it 7? Let's see what we can say about that. Now, what is f of 7? F of 7 is equal to the integral from 2 to 7 of g of t dt, which is equal to what? That's equal to the integral of, what do we already know? We know what the integral from 2 to 5 is of g of t to dt, plus the integral from 5 to 7 of g of t dt. The integral from 2 to 5, that's the same thing as f of 5, which we just said is 6.34. But what's the integral from 5 to 7? That is going to be whatever they say the area 4 is. That's 1.79. So what is 6.34 plus 1.79? Let's find out. That is 8.13. 8.13. So f of 7 is equal to 8.13. And let's talk concavity again. I think this is going to be concave up until about here. Let's, for simplicity, say that's x equals 6, because since the function g is increasing, I'm going to be accumulating area, and the rate at which I'm accumulating area is going to be increasing up to that point. So between, from here to about x equals 6, I'm going to have a curve that is concave up. And then it's going to come to a stationary point or a critical point, which I don't think I've done a good job showing. That's a little better. It's going to come to a critical point at, oh, no, it's not. It's going to come to a critical point at, actually, what do I show here? Yeah, it's going to come to, okay, so I'm second guessing myself. It's going to come to a critical point at x equals 7, because that's where g crosses the x-axis, which means I am no longer accumulating positive area, which means my function f should stop increasing. Okay, so I think I have a good graph on where I am going everywhere to the right of x equals 2. So now let's talk about how to go backwards. So let's stick with the crossings on the crossings of the x-axis. So now let's go backwards to 0.5. So what is f of 0.5? Well, we're still following this function. F of 0.5 is going to be equal to this. The integral from 2 to 0.5 of g of t dt. So it might look a little strange to see the upper limit of this integral be a smaller number. So let's change that. An integral property we know is that if you swap the interval, that just negates the value of the integral. So the negative integral from 0.5 to 2 of g of t dt is equal to what? That was actually something that was given to us as 6.6. So this will be negative 6.06. So if I go backwards, if I'm trying to find f of 0.5, so this value is going to be negative 6.06. So f of 0.5 is going to be negative 6.06. So I believe this is a point on my graph. So now let's talk about how I should connect this point that I just made to the point we already had at x equals 2. So over this interval, so basically to the left of this dashed line that I made a while ago, g is positive and increasing, which means we are increasing. Basically, our area is going to be increasing at an increasing rate. We should have something that's concave up all the way until we get to x equals 2, which we didn't think about at the time. That's actually going to be an inflection point. So here's what I'm struggling with. I'm trying to show that this is a critical point, and that's actually pretty good. So at x equals 0.5, that's a critical point. Why? Because that's where g crosses the x-axis, which means my function went from, basically my accumulator function f went from losing area, decreasing in value, to increasing, then accumulating positive area, so it's increasing in value. So now I think we have a good graph drawn from x equals 0.5 to x equals 7. So we have one more area to consider, and it looks like it goes back to f equals negative, or x equals -1. So f of -1, what's that equal to? That's equal to the integral from 2 to -1 of g of t dt. Let's do the same thing as last time. Let's switch the interval around. So that's from -1 to 2, the negative integral from -1 to 2 of g of t dt. But now I can break this down into things I already understand because I know what the integral was. So I'm going to break this down into the integral from -1 to 0.5 of g of t dt plus the integral from 0.5 to 2 of g of t dt. One of these things I already know because I just found it. What is the integral from 0.5 to 2 of g of t dt? Well, we said that was 6.06 because that's that portion of area 2. So positive 6.06. Then what's the value of the integral from -1 to 0.5 of g of t dt? That is going to come directly from the value of area 1, which I am hiding right now. That is positive. No, it's not. It is negative 4.29. So negative 4.29. So this comes out to be what? What is 6.06? 6.06 minus 4.29. That is 1.77, and I need to make that negative, so this comes out to be negative 1.77. So f of -1 is negative 1.77. So I have this value here. So again, last thing I gotta do is how do I connect those 2 points? So I'm gonna look for where this concavity changes, and it looks like again, the concavity is gonna change where my function g reaches a local relative minimum. It's going to be concave down up to that point, and then it's going to switch to being concave up. So I start off with this being a critical point because this is where function g is equal to 0. Don't be so picky, just let me draw. All right. Okay, so kind of a long-winded explanation there, but I hope the fact that we had to do, use the same properties a lot of times and a lot of different properties. And even though I made a lot of different determinations here, the logic I used, the reasoning I used to make those determinations, hopefully you saw a lot of commonalities between them, because I think there were a lot of commonalities there. But yeah, I think that's one way to approach question 4 here.